So, to compare between RLC and RLA, so this diagram will tell that. So, what I was telling that accumulator, so this is that 8 bit. So, when you are rotating left, so this is the rotation, the left rotation. Now, bit number 7, it will go to bit number 0 as well as it will go to the carry flag of the status register. So, both of them will get modified and all this bit 0 will come to bit 1, bit 1 will come to bit 2. So, entire thing is rotated left like this. On the other hand, this RAL, so this is also rotate left, but now this bit 7 will go to the carry flag and the carry will come to bit 0. So, this is a rotation through the carry. So, that is why it is called rotate through carry. So, carry is also rotated as part of it. So, other than that, we have got some more logic operations like compare. So, you can compare content of two registers or memory locations with the content of one register or memory location with that of accumulator. So, like you can, the general format is compare CMP register or memory R or M. So, the contents of the register or memory location will be compared with the content of the accumulator. And also there is an immediate version like CPI. So, compare immediate. So, here you need to specify one 8 bit number and the content will be compared, the content of the accumulator will be compared with this 8 bit number. So, this compare instruction, it will set the flags the Z, carry and sign. So, the 0 flag, carry flag and the sign flag will be affected. So, if the numbers are same, then this 0 flag will be set. If the comparison is done using this internal subtraction and does not change the content of the accumulator. So, it will do this subtraction A minus this what is the second operand R by register or memory or immediate value whatever you have specified. So, this based on that this operation will be carried out and accordingly these 3 flags will be set. So, if the result is 0, then this 0 flag will be set, that is if these two values are same. If a carry is generated, that means this if this R by M is larger, then this carry will be generated. So, in that case this carry flag will be set and the sign flag will be positive or negative depending on the result whether it is positive or negative. So, it will do that. Then we have got another class of operation which is this branch operation. And branch operation, so they are actually for transferring control from one memory location to some other memory location. That is, at present the program is executing at some point in the system, and so suppose these are the program lines. Now, at present the system is executing this particular instruction, then it is expected that the next instruction will be this one. But suppose this is the location say 1000 and this is the location 1001. So, after 1000 instructional 1000 is executed, the instructional 1001 will be executed. But due to some reason, so if I think that the next instruction to be executed is at location 2000, then from here this instruction should transfer the control from, instead of 1001 it should transfer the control to 2000 or sometime later. So, if you are trying to implement a loop, then it may so happen that this is the body of the loop, at the end of the body of the loop. So, you need to do the loop again. So, you need to jump back to this position. So, this way we need these branch instructions for doing this for implementing many of the control transfers. So, these branch instructions are used and there are two types of branch instructions. One is called unconditional branch, where the branching is independent of the outcome of previous operation, and there is a conditional branch. It is this branch will be taken if the previous operation it evaluated to some condition being true. Okay. So, unconditional branch is go to a new location no matter what, like whatever was the outcome of the previous instruction, it will branch to the new address and things like that. So, this unconditional branch instruction, so this is of the format the mnemonic is JMP, jump, and this address. So, address is a 16 bit address because 8085 supports 16 bit address. So, jump to a 16 bit address. So, when this instruction will be executed, I hope you can guess what is going to happen. The program counter will be loaded with the address that is specified here, so that the next instruction that will be executed is the from the address loaded into the program counter. So, here you see from the instruction register the value should go to the program counter, so that the program counter gets the jump address. Another instruction is call instruction. So, that is for subroutine, that is you want to execute a sub program. So, that is for call address, and there is a the return instruction to return from a subroutine. So, all these addresses supplied the address supplied to all branch operations must be 16 bit. So, they are all 16 bit addresses. So, at the end of the subroutine I should have a rate instruction. So, that will be returning from the subroutine, and this call instruction is for starting a subroutine. About the conditional branch, so we have got a number of conditional branch instructions like ZZ. So, jump on 0. So, if due to the previous arithmetic logic operation the 0 flag has been set, then it will jump to the next address that is mentioned. So, JZ address. So, it will jump to the specified address if the 0 flag is set. Similarly, we have got JNZ. So, it will jump if the 0 flag is not set. Okay. The 0 flag is 0, then it will be not of it will be jumping to that address. Then jump on carry. So, if the previous operation did not the previous operation had generated a carry, then this JC address. So, this will be jumping to the new address specified by this specified in this instruction. JNC is jump on no carry, then JP is jump on positive. So, if the sign flag is not set, then the result was positive. So, we have got the JP instruction for jumping on the result being positive, and JM is jump on minus. If the previous operation resulted in sign flag being set, the result was negative, then this JM address will jump to the new address. So, this way we can have this conditional branch instructions in 8085. Machine control instructions. So, we have got halt instruction to stop executing the program. So, when this is a special instruction, when this halt is executed, then the whole operation of the system will come to a stall. So, this is the system will be, so no more operation will be done by the processor to get the next instruction and all. Only thing is that you can send that interrupt to the processor now to take it out of this halted situation. And there is a no operation. Another very interesting instruction that we have is the NOP or NOP. So, that stands for no operation. So, what does it do? It does not do anything. So, it is used mainly for delay. Okay. So, if you want to put some small delay, so you can put this NOP instruction, and many times for the program debugging this NOP becomes useful. So, why? Suppose I have written some program. So, this is sorry. Suppose I have written a program in which we have got so this is the program I have written, and in this program I have this program is somehow not working correctly. I feel that the program is not working correctly. So, what I need to do is that suspend the operation of the program somewhere in between. So, what we do? We introduce some sort of special instructions which are useful for debugging, fine. So, and after that if you execute the program now, what the system will do is that when it reaches this point, the debugger will get invoked, and accordingly you can modify you can check the content of CPU registers or modify them and all those things. Now, while doing that, so your you have incorporated these instructions into the program, and this is this is done at the time of compiling the program itself or assembling the program itself. Now, later on when the program is working properly, then what to do with these instructions? So, if you want to remove these instructions, means you need to reassemble the program by removing all those places. So, a better option is later on you may also need this debugging. So, you just replace these instructions by NOP instruction, and NOP instruction code is 00. So, you can replace all these locations by 00, telling that it is a NOP instruction. So, that is useful, that is so if you have got some instructions introduced during debugging. So, you can later on remove them using this NOP type of instructions, and many of the debuggers have got these facilities. So, though we are in a basic course on microprocessors, so we may not be using that very much, but later on while working with some on some detailed larger programs. So, you may need to use this debugger, and there this facility may be useful. Another way of looking into the program, looking into the instruction, is the type of operands that are supported. Now, some of the instructions they do not have any operand. Okay. So, the operand is implied, like this CMA, the complement accumulator instruction. So, here the operand is the accumulator, but we do not need to specify it separately. So, that CMA is a 0 operand instruction or implied operand instruction. Then there are some of the operands are immediate in nature, like immediate data, like say ADI, add immediate 4F hex. So, we are telling that the accumulator should be added the accumulator should be added with the number 4F hex, and the result should be stored in the accumulator. So, here I am talking about some immediate operand, so that is called immediate data. Or we can have some internal register, like say subtract B, SUB B. So, we are subtracting the register B from register A, and that is another internal register. So, the register is an operand. So, we have got implied operand, we have got immediate operand, we have got register operand, and also we have got memory address as operand, like LDA 4000 hex, or the accumulator will be loaded with the content of memory location 4000. So, here this 4000 hex is a memory address that we need to load. So, this way we can think about we can talk about the type of operands that this 8085 instruction set has, and for that matter any processor design that you look into. So, we have to look into we can categorize these instructions based on the operand types. Size of the instruction, like so far we have assumed that all instructions they are of same size, but does not it look a bit odd? For example, if I just go back and see this instruction is CMA, I do not need to specify anything after this, and this instruction is ADI 4FX. So, I have to somehow tell the number 4F. So, if I say that certain number of bits are dedicated for storing this opcode part, so that is true for CMA, that is true for ADI, that is true for SUB, that is for LDA. So, those bits are already taken up. Now, this 4F has to be stored separately, this B has to be stored separately, this 4000 has to be stored separately. So, if I give say this instruction 8 bit for coding, then this CMA has got an 8 bit code, then ADI 4FX it cannot be an 8 bit instruction, okay, because this ADI part itself will take 8 bit and this 4F will take another 8 bit. So, this is expected to be 2 byte instruction or 16 bit instruction. Similarly, this LDA, so apart from this code of this LDA, so I need to specify a 16 bit number 4000. So, it is all likelihood, so this will be a 3 byte instruction. The size of the instructions are not same, depending upon the type of the operand, the size of the instruction may be different. So, that is what we are going to look into next. So, depending upon the operand type, the instruction may have different sizes, and as a result it will occupy different number of memory bytes. Typically, all instructions occupy 1 byte only, because that is the opcode part has to be coded and the opcode should be 8 bit. And so, the exception is that with the instruction that contains immediate data or a memory address. For immediate data, we have to have another 8 bit value. Okay. So, that is why the instruction will be 2 byte instruction, where the second byte will be holding the immediate value. And in case of 3 byte instruction, the memory address, so the instruction has to be 3 byte wide, because the next 2 bytes will be holding the 16 bit address. So, that way it has to be a 3 byte instruction. So, instruction size will depend on the number of operands that we have in the instruction. So, let us look into some example. So, load an 8-bit number into the accumulator. So, the instruction is MVI A comma 32. So, what is the operation? Operation is MVI A. So, for MVI A, since this is the operation, I can allocate one of those 246 codes that 8085 supports to MVI A. So, processor 8085 designers, they have given this some code to this MVI A, and that code is 3E. So, 3E is the code for this MVI A. So, the next operand is the number 32. So, this 32 is the next operand and it is taken as hexadecimal number. So, this is the hexadecimal number 32, that is the second byte. So, this MVI A comma 32 will be represented by a 2 byte instruction, where the first byte will be 3E, second byte will be 32. So, how the processor will execute this instruction? So, when the PC will put the memory address onto the address bus and give the ALE signal. So, this 3E value will come to the data bus and it will reach the instruction register. So, that will go to the instruction decoder. By looking into this 3E, the processor, the instruction decoder will understand that this is an MVI instruction. So, another byte has to be fetched from the memory. So, now it will again put a memory read request onto the memory and with the address already incremented by 1. Whenever this location has been accessed, the program counter has already been incremented by 1. Now, program counter points the next memory location which contains the value 32. So, memory read is done and the memory will put the value 32 on the data bus. So, this will again come to the instruction register and from there this 32 will go finally to the accumulator during execution cycle. So, this is how this operation will take place, this MVI A comma 32 operation. Another instruction example is say go to address 2085 and the instruction is jump 2085, JMP 2085. Opcode is JMP, operand is 2085 and the code for JMP is C3. So, the first byte will be C3, second byte will be holding 85 and the third byte will hold 20. Why is it like this? Because Intel follows the convention that for whenever we have got memory words, whenever we have got words of more than 1 byte width, then the lower order byte should go to the lower order address, higher order byte should go to the higher order address. Now, if this is the first location, say this is the location 1000, then the next location is 1001, next location is 1002. Now, when I am storing this 2085, so 85 is the lower order byte, that should go to the lower order address, that is 1001, and this higher order byte, that is 20, it should go to the next higher order address, that is 1002. So, memory location 1000 will get C3, 1001 will get 85 and 1002 will get 20. This is how this coding is done. So, if you are trying out some hand assembly or if you are looking into the assembled file generated by any assembler, you will see these things that the higher order byte has been put in the higher order address space for those things. But it is not uniform, like say some other processor may do it in other way, but 8085 does it in this fashion, the higher order byte goes to higher order address. Now, there are different ways by which you can give the data of an instruction, like these are called addressing modes. So, addressing modes means how many ways I can tell the operand for an instruction. So, 8085 has got 4 different addressing modes. They are called implied, that is we do not have any other operand separately. So, the instruction itself tells what is the mode. Then immediate, so immediate some 8-bit immediate value is given. Direct access, so that the address is mentioned directly, or there is indirect memory access, which is or indirect addressing mode, which is giving some say pointer sort of thing. Okay. So, the one is direct, that the address value is specified in the instruction itself, and in the indirect address the address part is not directly mentioned in the instruction, but whatever operand is told in the instruction, that will contain the address, like LDAX B. So, the BC pair will hold the 16-bit address that has to be used for getting the content of memory location to be loaded into the accumulator. So, this is how these addressing modes are supported in 8085. So, if you look into more complex processors, you will find that there are many other types of addressing modes that are supported, but 8085 being a very simple processor, so it does not have more complex modes. Data formats. So, if you in 8-bit microprocessor, so we can represent data in different formats, like we can represent the ASCII in the ASCII format. For say, I can all the anything that we are talking about is nothing but a character. So, if I say like that, then each character can be coded into an ASCII code. So, there is standard ASCII codes are available, and ASCII codes are 8-bit wide or 7-bit wide. So, that can be used for this storing the data, representing the data, or I can have a binary coded decimal. So, for example, binary coded decimal means, so I for storing the number say 25, sorry, for storing the number say 25. So, I can have in a binary number system. So, it will be, this is the value 25. Okay. Now, so in so now if I am talking about an 8-bit representation, sorry, so this is 0 1 0 0 0 1, and before that I should have 2 more zeros. Okay. So, these 4 bits, this is 4 bit, this is 4 bit. So, that makes it binary, this makes it binary 25 in an 8-bit notation. Now, this BCD code will tell that I will consider this part as a separate digit, these 4 bits as a separate digit, and these 4 bits as a separate digit. So, this becomes, so this part is actually 1 in decimal, and this part is also 1 in decimal. So, 25 if you are representing it in BCD form, so it will be 1 1. So, that way also we can represent the numbers. So, for the, this is particularly useful when you are trying to display the numbers. Okay. So, that becomes helpful in many cases. So, we will come to this BCD format later when we look into some programming examples. So, we can have signed integer or we can have unsigned integer. So, signed integer means integer with some with positive or negative, and unsigned integer means they can be only positive values. So, whatever microprocessor will understand, so it will be consisting of zeros and ones only, and it deals with the values as strings of bits only. Okay. And so, as a user, so for the user the bit string has got different meanings, like whether it is signed integer, unsigned integer, BCD, ASCII, whatever. So, this is for human interpretation. As far as the processor is concerned, so this is nothing but a string of zeros and ones. So, for example, suppose the accumulator has got the value 0 1 0 0 0 0 0 1. Now, if it is to be if it is an unsigned integer expressed in binary, so this is the equivalent to 65. Okay. Now, if you are interpreting it as a BCD number, binary coded decimal number, then as I said that the each 4 bit is constituting 1 digit. So, that is first 4 digit is 4, with this first 4 digit here. So, 0 1 0 0. So, this will make it 4 and this will make it 1. So, this 41 is the BCD number for the same bit string. And if you are looking into the ASCII code, now this 65 is the ASCII code of A. So, you can also say that this accumulator is storing the character A. Okay. So, if it is a string of zeros and ones where the 0th and 6th bits are set to 1 and while the all other bits are set to 0. So, if you just take it as a bit string, then I can say this is a bit string where these 2 bits are only 1 and rest of the bits are 0. So, this way interpretation varies from the human understanding point of view, but as far as the system microprocessors understanding is concerned, so it is nothing but a bit string only. Next, we will go towards implementation of counters, because many a time what happens is that we need to have some actions done repetitively, and we will like to implement some counters in the programs. Okay. So, a loop counter, so you can implement these counters very easily in microprocessors or say 8085 by loading a register with some value and go on decrementing the register till it becomes the content becomes 0, or you go on incrementing the register till the content overflows and comes back to 0. So, a loop can be set up with a conditional jump instruction to loop back, and it is when the count becomes a particular iteration count or termination count, then the loop will terminate. So, this way you can represent some counters. So, the typical counter structure body will be looking something like this. So, it's first there will be some initialization, then body of the loop, then update the counter. So, have we reached the final count? If it is yes, it will come out, and if it is no, it will go back to the body of the loop. So, this way this loop counter is implemented, loop counter is represented in the form of a flowchart. So, we will see how these are implemented in programs. So, this is a very simple assembly language program for implementing loops with the DCR, decrement register instruction. So, here what is done is, first this MVI C15 hex, that means this C register will get the value 15 hex. Then this decrement C, so decrement C instruction, so this will decrement the value of the C register. So, from 15 hex it will become 14 hex, 13 hex, like that. First it will become 14 hex, then we check this flag. So, because of this decrement operation, this status register, the flag register will get affected, and since the value is still positive, it is not yet 0. So, jump on not 0. So, this will be true, and this will go to, this says that jump on not 0 to address loop. So, it will come back to this line and it will again do a decrement. So, this way it will go on decrementing and checking whether the value has become 0 or not, and when the value becomes 0, at that time the 0 flag will be set. So, next time it checks this JNZ. So, this 0 flag is set. So, it will not be going to this instruction, but it will be coming back to the next one. So, this way you can implement a very simple loop by using this decrement, decrement and jump instructions, and this is helpful for implementing some small delay. Okay. So, for example, if you have outputted some pattern onto this LED and some LED display, and human eyes will not be able to follow if it is changed very fast. So, you want to put some delay for eyes to understand the display. So, we can put some delay by putting this type of delay routine, and then after that we can change the pattern, change it to the next pattern, so that it can it will be able to show this show the next pattern. So, that display becomes stable. We can also use register pair as loop counter. So, in the previous example that we have taken, so here it is only the maximum delay, maximum looping count is 255 only. So, if you want to change this value, then we have to use a register pair for this loop. So, because if you use a register pair, then I have got a wider range, because with a 16-bit value, so the maximum value is 65535. So, I can have a larger range of this looping. But there is a small problem, because now we have to decrement this when you do the decrement operation by DCX instruction or increment operation during the INX operation. So, DCX and INX, they do not modify the flag. So, this is a special thing, that the DCX and INX instructions, they do not modify the flags. However, there can be some other tricks by which we can correct this problem, and we can correct it by taking the OR of two registers, this like DC. So, the DCX, so if you are using say BC pair, then we can OR the B and C registers after doing this decrement operation, and if both of them have become 0, then the OR of them will become 0, and this OR instruction will affect the 0 flag. As a result, we can detect the situation that the counter has underflown.